Hello and welcome back to my channel. Keeping for a while the ongoing Conquiz series, today let us explore something new, exploring statistics part 1. Why statistics? Well, a single line answer: because statistics are an inseparable part of our lives, right? You know, and today we'll be discussing something very special, important in statistics. And what's that? Well, it is regression for a linear statistical prediction by applying least squares. Most of the time, you know that when we do some experiment, we observe some dependent variable, say y, as a function of independent variable, say x. And if x and y are linearly related, they have a linear relationship, then what we expect after getting the experimental points, if you draw the line, you should get a straight line, a perfect straight line where all the points are on the lines. Would you expect? No. For example, here the data are given for resistivity of some compound as a function of temperature in centigrade scale. So these are the data given here. And if you plot this rho versus t, the points are like this. So they are following almost a straight line, but not really one. For example, another example, Cp versus T, the points are, of course, they are giving a straight line, but not all the points are on the line. Why this is so? Because as you know that even if x, you are very sure about the uncertainty of x values, but it's not under your control actually, the certainty of y values, because some indeterminate random errors must be there, which is beyond your control. So that's why the points are not on the line. And regression's job is to give a best possible straight line, y equal to b plus mx, where slope m is called the regression coefficient, so that it can explain the variation in y as much as possible. So that's why I call best fit. Okay, we'll understand why it's called best fit, in what sense. So let us go for the next slide. Before I go into the details of this method of least squares for this linear regression, a few words on regression and correlation. It's based on two assumptions. The first one, there must be a linear relationship between x and y, and indeterminate or random errors are there only in y and not in x. Otherwise, if both x and y are taken as random variables, then we need correlation analysis. Regression is not enough. And another point, if y varies very significantly with x, then we need a little bit of modified least squares. We call it weighted least squares method. Well, so all the points are not on the line, right? So they are a bit scattered, deviated from the line. So suppose this point, it's a magnified version. So this point is not on this least squares line or regression line, and this vertical distance we call residual. So it's a distance between yi, that means the experimental observed value, minus this y value, which is nothing but the mx plus b, that is the regression line. So the difference is called residual. So it will be even more clear from the next slide. Well, these d 1, 2, 3, 4, 5, 6, these are the residuals, and you see the way we have defined this residual, the line points are, some of the points are above the line and some of the points are below the line. So that means the residuals can either be positive or negative. So if you are concerned about the total residuals, if you just do the sum of these residuals, it will be quite misleading, because of the positive and negative values for mutual cancellation, the value of the total residuals may be very small in spite of the fact that the points are very much scattered, right? So only the sum is not enough. So what we do, this method calculates the best fitting line for the observed data by minimizing the sum of the squares of the various vertical deviations. So sum of the squares, right? That we want to be minimum, right? And that we do by least squares method. So more categorically, what we do, the least square method finds the sum of the squares of the residuals. We call it SS sum squared, residual, and minimizes the sum using calculus. That I am coming in a while. But for mathematical simplicity, the value of this SS resid, okay, for that and for the rest of the calculation, we do some convenient summation SXX, SYY, and SXY. That what they are, I am coming in a while. But SS resid is defined in this way, that it is the deviation of the ith point and then its square and then summation over all the points, right? So that is how we define SS resid over n is the number of points. Okay. And what is the application of calculus for minimizing? That's the minimum maximum problem everyone knows. What we do, we evaluate SS resid and then we differentiate this function with respect to the two unknown m and b, that is in the regression line. They are unknown to start with, and setting these derivatives equal to 0. That is the condition for minima. This operation yields naturally two equations because two unknowns are there and are called normal equations in the two unknowns m and b. These equations are then solved to give the least squares best estimates of these parameters m and b. Well, how do you define the sums that I mentioned, S, X, X, Y, Y, and X, Y? That's simply like this. So it's a, again, all are square terms. This is the product one, last one. So it is the difference between the ith x and the average x and square and then summation. And it can be shown that it becomes even more simple for calculation purpose. Similarly, yi minus y average square summation, and xy is x minus x average into y minus y average sum over all the parts. Okay. So these are the definitions. We need to evaluate, if you notice carefully, that we need to evaluate sum of xi values, sum of yi values, sum of xi square values, sum of yi square values, right? For quantity and this product finally. Okay. Oh, another is sum of the product x, y. So 5 quantities we need to calculate for the given set of data. Next, y average and x average, as obvious that x average is nothing but sum over xi by n and y average is sum of yi by n. Actually, this xx and syy, they are connected to variance in x and y respectively, and finally the sxy is connected somehow to the covariance of x and y. So I am skipping the detailed mathematical part of that solving that minimizing procedure, but after doing all this and after solving the last two normal equations, finally we get the two parameters that we want, the slope m and the intercept p, in terms of those sum terms sxy, sxx, and this is the second one. It's quite obvious. We are not calculating any new thing, but supposing and it can be proved that the best fit line always passes through the average point x bar y bar. So if we just put x bar and y bar in equation, after knowing m, of course, you can calculate the factor b. Well, so far so good. But if you use a standard package, say for example Excel set or something like that, they report it automatically, this m and b, but along with these two parameters, they also give something more. What is that? Some r square term. And we ask our students to report that value also, and we give some marks in exam for this r square value. And if r square is very close to 1 or 0.98, 0.97, etc., then we say that okay, your curve is good enough. That means somehow r square measures the goodness of the fitting. But without knowing much, we tell our students that it is good, without answering or explaining that what this r square is all about, how it measures the goodness of the curve, and what do you mean by the goodness of the curve? How do we calculate r square? What is the significance? So these are some unanswered questions today we would like to explore in coming few minutes. But before that, let us see an example of the least squares method. So carry out the least squares analysis for calibration data for the determination of isooctane in a hydrocarbon mixture provided in the first two columns. So our x and y values are nothing but the mole percent of isooctane xi, and the peak area is yi. So sum over xi, sum over yi, we need 5 quantities as I mentioned, sum over xi square, sum over yi square, and sum over xi yi. So these 5 summation are needed for our final calculation. So let us see what we do then. So we need to calculate the s, xx, yy, and xy, and they are calculated using the values in the earlier slides. So they come like this, and finally the aim is xy by xx. So xy is this one, and xx is the first one. So 2.39 something by 1.1457, right? So this sxy divided by sxx, that gives you the slope, and that is 2.09. And if you put it here, y average, x average is known because it is sum over x by sum over y by n number of points, and this is sum over x by n into m. M is already calculated, so you get finally the intercept b 0.26. So finally the equation regression line, what we call, or least squares line, is y equal to mx plus b, so 2.09x plus 0.26. So this is the regression line, and it is the best fit line because it gives you the minimum sum square of residuals. Okay, it is resid. Well, come back to the point of r square. So if we try to interpret the least square results, what it tells, the closer the data points are to the line predicted by a least squares analysis, the smaller are the residuals. That's quite obvious. The sum of the squares of these residuals, this is resid, measures the variation in the observed values of y that are not explained by the presumed linear relationships between x and y. So I repeat it, that because SS resid gives a measure of how scattered the values are, y observed yi, how deviated from the least square line. So naturally, more the deviation, that means less it is explained. So somehow this SS resid does explain the variation in y that are not explained by the line. Okay. Now we will define another SS. We call it SS total, SS tot. And here SS tot is a total variation, right? Because it is evaluated y, since it is observed values y, the deviations are measured from the mean value y. So yi minus y bar, not y calculated regression, but y by yi minus y bar. So this is the worst possible sum squared, and it includes both the variation in y explained and the variation in y not explained. So that's why it's called total variation, right? But I am interested that how much it is explained. So far we have got how much not explained and how much total. So it is simple to answer that how much it explains. It is a subtraction between these two quantities. You subtract SS resid from SS total, so gives you what we may call SS regression, and that is the measure of variation in y which are explained. Okay, so that is we are interested in, that how much it is explained, and that is SS regression. So if I are now interested that what is the fraction, of the observed variation in Y, that is explained, okay. And that is very simple, because if you get the amount explained SS regression and you divide it by the SS total, that would give you the fraction. So it SS regression divided by SS total, and that is called the fraction, and it's called as coefficient of determination R square. So that is R square. It is a fraction of the observed variation in Y, that is explained. So R square is this fraction, SS regression is SS total minus SS recede by SS total. So SS total by SS total is 1. So it is 1 minus SS recede by SS total. So final formula becomes R square is 1 minus SS recede by SS total. Okay. Though very often we use some another formula that's equivalent, that we'll see. But before that, let us consider two model data set and their plots. So it's the first set, and it looks that the points are okay, not that scattered. This black one is the mean line, and the blue one is the regression line or least squares line. So from that model data, if we calculate the SS total, SS recede, actually they are here given by new name, variation mean, variation line. Actually they are nothing but, as I mentioned, that they are connected to variance. This SS total is variation mean, SS recede is variation line. So total minus residual by total. So for example, it is 32 and 6. So it gives you 0.81. So that means here the conclusion that the XY size and weight here, the XY relationship accounts for 81% of the variation. What relationship? The relationship that is predicted statistically by least squares method, by regression line. So that relationship accounts for 81% of the variation. So this is just for a model example. Similarly, this second set, obviously the points are much scattered, right, from the both mean line and the regression line. So what we expect here, let us see. Here the data value are 32 and 30, SS total and SS residual. So by definition, R square gives you 32 minus 30 by 32, and that is 2 by 32.06 or 6% only. So the relationship accounts for only 6% of the variation. Okay. So let us see now the another formula that often used, and it can be shown by using the same sum terms, that R square can be given by S square XY by S XX and S YY. So all the terms are here. Okay, the same terms, only the formulas look slightly different. And one more thing, it can also be shown that SYY, by definition, the way we have explained or defined, SYY is greater than equal to this first part, S square XY by S XX, and it is in the denominator SYY. So this SYY is greater than, and it is in denominator. So the overall right hand side of this equation is less than equal to 1. That means R square is less than equal to 1, or minus 1 to R1 is the range of R. Okay. Now the question we may ask that when R square is 1, and what does it signify? Similarly, when R square is 0, and what does it signify? So before we answer these two conceptual interesting questions, let us see a few more points, that R square or R. In some textbooks they mention R, in some other R square, and some other text both R and R square. But personally I feel that R square is a better signifying term. With a model example, suppose again we have taken two model data set, and corresponding R values is 0.7 and 0.5. So from detailed analysis, we know, supposing that we know that the first set is twice as good, the first set fitting is twice as good to that of the second set. But the R value 0.7 and 0.5, the ratio is 1.4, not 2. So it says that it's 1.4 times as good, but not twice. So it is not obvious that a regular R 0.7 is twice as good as R equal to 0.5. But actually it is supposed to be so for this model example, though I am not showing with the data. But now you see, if you make it square, R square, so 0.7 square is 0.5 and 0.5 square is 0.25. So now the first set fitting R square curve is twice to that of the second set, as we expect. So it's just an example that why it is more meaningful to report R square and not R. Well, let us answer the questions now. When R square is 1 and what does it signify? Well, let us start from the definition of R square. So, of course, when it is 1, if SS residual is 0, then 1 minus 0, so it's 1. So, when SS residue is 0, it's a sum of the square term. So, definitely each individual term within this third bracket must be 0, right? So, that means yi minus b plus mxi is 0. That means the difference is 0, difference between the observed value and the point on the line. That means the point is on the line. Which point? Ith point, and for all I. So, all the points are on the regression line. If it happens so, then R square is 1. But very often it doesn't happen. So, R square is very close to 1. That's why you call that the closer R square is to unity, the better the linear model explains the y variations. So that's why we tell our students that if it is 0.98 or 0.99, then it's good enough. So this is the secret, as I've explained. Okay. And when R square is 0, what does it signify? Let us take help from the second definition of R square. And obviously, R square is 0 if this S square xy is 0, right? And Sxy is given like this. So, if Sxy, this Xy is 0, then of course R square is 0. But when it is so, let me explain. If there is no relationship between the x and y, supposing they are not at all related, then there is no binding for y to be somehow related to x, because they are now free, they are not biased. So, the xi minus x bar and yi minus y bar, they may be positive and negative, and since they are not bound by any relationship, they are not related. So, it is very likely that they are equally likely to be positive and negative. So, each term of this summation equally likely to be positive and negative, and that thus by cancellation the sum Sxy itself becomes 0, and hence R square is 0. So, we conclude that in that case x and y, that means when R square is 0, then x and y are uncorrelated. So, that is the conclusion we can make from here, uncorrelated. Let us now see our example from the previous one. We have already seen that our best fit line or regression line has come like this, 2.09x plus 0.26. And then what we need for this calculation, for R square calculation? We need, you see, for each value of xi, we can find a predicted value of yi from the linear relationship, because that is now known. And let us call this predicted values yi as yi hat. And we can write yi hat as b plus mxi, that is known, to make a suitable, make a table of the observed y values, the predicted y values, and the residuals, and then square of this residual, and then you make a summation of these residuals to obtain SS residual. So it will be very clear from the table in the next slide. So these are the x values This is the y values, observed y values, and this is the predicted from where? From this line, because if you put it x here, you will get some y which we call y hat. So this is the predicted y values, and you take the difference, so you get the residual and make it square, and then you make it sum. So that is the SS residual, or you can call it SSYY also. So now what next? We have already SYY is this, actually this is already calculated, and this is SS residual. So the formula is 1 minus residual by total. So residual is 0.06, 0.0624, and total or SYY is 5.0774. So it gives you 0.9877. So what's your conclusion? Your conclusion is that this calculation shows that over 98% of the variation in peak area can be explained by the linear model. So that is the conclusion and significance of what R square is. Okay. So let us apply the second formula and see whether the same results is coming or not. This time the formula is like this, and you are using the same values that we have already calculated and we have already used. So it is R square is SXY square. Now XY is 2.39 something square by SXX and YY. So this one and this one. So again you see the result is 0.9877, exactly the same that we got from earlier formula. Well, this is an exercise given for the audience. So please keep track of that, give pause, record it, note it, and find the regression line as well as the value of R square. The answer is also given, and finally you have to interpret the result. So far so good. We have studied the linear regression, but the question may be raised here that can we apply this linear regression method for even a set of xy which are not linearly related? In some cases, yes, we can, but for that we have to linearize the nonlinear part. So these three examples, of course, here you see y and x how they are related. It's not obviously they are not linear relationship, but the expressions are so that we can transform to linearize to get new variable, maybe x to x prime or y to y prime, or both x and y to x prime and y prime. So in the first case, if you take log, then your ln y, that is your new y variable y prime, and that ln b plus mx. So now if you make a linear regression of not x and y set, but x and y prime set, and that's linear, and the slope m of this regression, you get directly this m unknown, and b how you can get? From ln b, that means the intercept of this linear regression, you can calculate the b, right? Intercept equal to ln b. Okay, so b is e to the power intercept. Similarly, in the second case, here you have to take y prime and x prime both by taking log, and the linear relationship looks like this. So here again you get m directly, but b is slightly by log calculation. Okay, and the third example is the reciprocal. So it's simply you take 1 by x to be your x prime, and the linear relationship comes like y equal to b plus mx prime, and you get m and b accordingly. Okay, so these are left for exercise to understand it more, and maybe a few more examples from different texts. So thanks for watching. Our next video would be coming soon on statistics part 2, but I would request you that what particular topic we should come with, you can make suggestion, and not only that, on this present video you can make suggestion, comment, remarks, criticism, praise, whatever you think, to make it a better presentation for next time for my students. So thank you very much. Till then, please keep on watching, do subscribe, and encourage your friends to subscribe. Thank you.